Hello, I'm Stephanie Marcus from the Science, Technology, and Business Division here at the library, and I want to welcome you to the 13th year of our collaboration with NASA Goddard. This is the first of our lectures for 2019, and we have 7 others scheduled. So there's a list out at the table, and you can always check our website in case there's something wild that happens. I haven't looked over my remarks, but the last time Dr. Petro was here, he talked about the last men who walked on the moon. That was Apollo 17. And he also told us what was going on at that time with the Lunar Reconnaissance Orbiter, which has now been up almost 10 years. So we have a lot more to learn. Today, we're going to talk about the first men on the moon. And as I said, what's going on with the LRO. Dr. Petro was interested in the moon as a child. He has a family connection, which I'm sure he wants to mention. Maybe those of you who were here before remember. And he was also interested in geology. So in college, he was able to combine the two and become a planetary geologist. And he is the project scientist for the LRO. Last time you were the deputy, right? Yes, he's moving up. I just wanted to mention that actually it looks like a good number of you might have watched the first moon landing on TV. I thought we'd have a lot of those kids who missed out on that, but that's the one perk of being a senior. You have all these cool things that happened. So please help me welcome for the second time, Dr. Noah Petro.
Well, thank you very much for having me come back. As I said earlier, it's very rewarding to be asked to come back to do something because at least it suggests the first time wasn't so bad. So hopefully there'll be a third time. We'll see how the next 45 minutes or so go. Now, in doing my survey of the room, I'd say about 10 or so people might have been, 1 or 2 years old at the time of the moon landing. And so just as a sort of a refresher, we're going to look back over not just 50 years, but a little bit more than that. What was leading up to Apollo? What was Apollo 11 and what came back? And my goal is to talk a little bit about how we used what Apollo 11 did as a template moving forward. As many of you probably are aware, we all learned a few weeks ago that NASA's got the new objective of landing humans at the South Pole by 2024, which is a very interesting goal. And a lot of people, including myself, are working very hard to realize that. Fortunately, we have pretty much the best example of how to conduct human exploration on the moon in the case of the Apollo missions to the moon. And so ultimately, we all go back to what was done 50 years ago as not just inspiration, but really as the template of how we move forward. Just as a sort of a touchstone for what I'll be talking about today, and in looking at the upcoming presentations that are scheduled in this series, I was impressed not at just the quality of the speakers and the topics, but also at how impactful Apollo is in all of these science presentations. There's one in particular that caught my eye. A colleague of mine, Dr. Jennifer Eigenbrode at Goddard, we talking about the discovery of organic matter preserved in 3 billion-year-old mudstones on Mars. Now, that'll be a great talk about the search for life, but one of the things that caught my eye on that is this idea that it's 3 billion-year-old mudstones on Mars. And you ask the question, how do we know that those rocks on Mars are 3 billion years old? Because we went to the moon. And so hopefully what I can leave you today with is not just a sense that we went to the moon and we accomplished a lot of things, but by going to the moon, we opened up this window into the rest of the solar system. And as we find solar systems elsewhere in our universe, all of our understanding for how those solar systems work, how the planets in our own solar system work, comes through the lens of what we learned because we sent humans to the moon 50 years ago. Apollo 11 had a very simple goal, and I think we're all familiar with it. Nothing more, nothing less. The objective of the mission was to land men on the moon and return them to the Earth. That was it. There's no mention of science. There's no mention of collecting rocks. Very early in the mission development stage for Apollo 11, there was going to be one astronaut that got out, scoop up some sample, plant the flag, say a few words, get back in and come home. As late as 1968, late 1968, that was what Apollo 11 was going to look like. And it took the efforts of many scientists working within NASA to push harder to get 2 astronauts to go out. Now, why 2? Well, with 2 astronauts, they could do not just twice as much, but one could set up science experiments. They could spend more time collecting samples and begin to eke out just a little bit of science in this first this first landing on the moon. But of course, human safety, crew safety was the first and most important objective. The fact that the crew came back healthy, safely, was mission accomplished. Everything else was sort of gravy on top of that. How did we get to the moon? I'm a geologist by trade, but I love space history and reading about it. And Apollo didn't just start when Kennedy gave his famous speech to Congress in 1961. Really, the seeds of landing and sending humans to the moon go back to 1955, where there were studies of what would it mean to have a huge, gigantic rocket, not just for purposes of warfare, but for space exploration. Of course, everything kicked into high gear with the launch of Sputnik in 1957, and the space race was, of course, then on. In 1958, the U.S. responded with Explorer 1, the first U.S. satellite, and by April, at that point, the Air Force decided that it was time to start seriously mapping the moon. I think early on it was recognized the moon is not just a nearby celestial object, but a destination, a target. And so it was time at that point to really turn into high gear this idea that, well, eventually we're going to be going there. We don't know when, but we'll need to know where to go and what to do when we get there. And of course, we've been commemorating the 60th anniversary of NASA as well recently. And so in October of 1958, we marked the official birth of NASA. And then soon thereafter, the selection of the first group of astronauts. And I'm sure if you asked any of the 7 of them, they thought they'd be the first men to walk on the moon. The first mission to the moon comes in September of 1959, Lunik 2, the Soviet mission, which crashed on the moon 35 hours later. And finally, in October of 1959, we have the first images of the far side of the moon. And I think that's one of those turning points where, as much as it's perhaps Soviet propaganda to image the far side of the moon, it also becomes this incredible scientific accomplishment to start to study surfaces that have never been viewed by humans. And so, as much as there's military and nationalistic events going on in here, science begins to bubble up. Now in 1960, January of 1960, the follow-on to the Mercury program, this was before Gemini was even envisioned, Apollo was selected as the name of this 3-person program to go to the moon. Later in the year, there were guidelines set about in terms of what this program would look like, what it would feel like for the astronauts. And finally, in July, just about 9 years prior to actually 9 years and a day before the Apollo 11 crew returned to the Earth, Apollo is named as the next, that version of human exploration. Then 1961 comes along and things get really busy, of course. Yuri Gagarin orbits the Earth, which was a wake-up call throughout the U.S. We were not ready at that point to send humans to space, and so there's a very busy month. JFK responds, and there's this great NASA document that outlines this month essentially through the memos, the material. JFK contacts his vice president and says, what can we do that will beat the Russians where we win? We have to do something that will surpass what their capabilities are. A week later, LBJ writes back after having contacted NASA leaders, particularly Wernher von Braun. Well, looks like exploration of the moon is probably the one thing that we can do. Notice the word propaganda value. At that point, we're going to do something to beat the Russians. It's going to be big, it's going to be loud, and we have a chance of doing it, and we could probably do it by 1966 or 1967. Now, 1967 should be an important date in this initial race to the moon. As was mentioned earlier, my father was an engineer on the Apollo program. He built parts for the lunar backpack and for the lunar module that sent astronauts to the moon. His responsibility was keeping them alive. And so the few times that he's been fortunate enough to meet these astronauts afterwards, he'll say, oh yeah, I built the parts for the portable life support system. And they always, oh, that works so great. Thank you so much. And he says, well, okay, thank you for making me look good. His management, his direct supervisor, said that we have to be ready to send humans to the moon by November of 1967. Why November 1967? That would have been the 50th anniversary of the Russian Revolution. And at the time, there was a recognition that, okay, maybe the U.S. is in it for propaganda value, but certainly the Soviets were as well. And if they were going to do something, certainly Sputnik in 1957 as a celebration of the 40th anniversary of the Russian Revolution, we have to be ready for the 50th anniversary. And so they were using not just the decade, the end of the decade, as a goal, but using November of 1967 as a target. for having something ready, something big to do. A day later, Werner von Braun writes back to LBJ, we certainly can beat the Soviets, and we have the opportunity for the first landing of a crew on the moon. And then he also puts in parentheses, including crew return capability, of course. So he also is fully aware that we have to bring them back safely. But that plants that seed that eventually comes into the speech that President Kennedy gives just about a month later, after one astronaut spends 15 minutes in space saying, we're going to go to the moon, astronauts on the moon back by the end of the decade. He sets that goal. It's very clear, very well said, and very clear that they're landing a man on the moon and returning him safely to the Earth. And that's it. And that's Apollo in a nutshell. Again, at no point do we talk about science. All of the science, all the advances come later. But if you want to point to a moment where Apollo not just is named and envisioned, but given wings, per se, it's that, of course, that date on May 25th. Now, over the intervening 8 years or so, a lot happens. Of course, the Soviets have their successes and their failures, as does the US. And the space race is on. Now, there's a lot of things that I could say, but I always like to use video clips because other people have said it much better than I. So I'll allow President Kennedy the chance to explain why he wants to go to the moon.
Many years ago, the great British explorer George Mallory, who was to die on Mount Everest, was asked why did he want to climb it. He said, because it is there. Well, space is there, and we're going to climb it. And the moon and the planets are there, and new hopes for knowledge and peace are there. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked. Thank you.
Now, if you've never watched or listened to the whole speech, it's about 18 minutes. I, like many of you in the room, I'm a commuter here in DC, 45 minutes roughly from Alexandria to Greenbelt. And so I'll listen to my podcast, and every once in a while I'll say, I don't want to listen to any news, I listen to that speech every once in a while. It's just a little insight into my unique brain. But what I find so fascinating about it is he mixes in not just humor, but also this vision of what he wants it to be. Now, there is some discussion of how serious he was about it, how much he really thought it was worth it. It was going to be expensive. In his speech, he talks about how expensive it's going to be. He also says that it costs the U.S. taxpayers less than is spent annually at the time on cigarettes and cigars. I'm not sure how that would translate to today. But he sees the value in it. But again, not mentioning science. But he does talk about, in that speech, we had just launched a mission to Venus, and that he viewed space as being something that should be used for peaceful purposes and for the science advancement. So this is a year and a half later than his speech to Congress, and so at that point he's beginning to bring in the idea that science has something to benefit, that humanity has something to benefit from these explorations. So I'm going to talk about the 3 stages of exploration and how it serves as a template for today. First, the preparation, everything prior to Apollo 11's launch. There was, of course, the financial and staffing investment. It wasn't just my father that was working on Apollo for a period of time. It was about 400,000 Americans. The planning and mapping as a scientist, what did we have to do to prepare for humans to go to the moon? And then, of course, a bit of the training. And each of these 3 kind of issues of preparation are relevant today. We have to make financial and personnel investments in exploration. We have to prepare and map and plan where we go on any planet, and then of course training the astronauts for what to do when we get there. And then there's the 8 days of participation, the 8 days of the mission of Apollo 11. Of course, we have the 3 crew and the thousands of people on the ground supporting them. And then the payoff. After July 24th, after that splashdown in the Pacific Ocean, there's the payoff. And who benefits from that? I say all of humanity. It's where we entered a completely new era of not just science, but of human existence. Having sent people to another celestial body, returning science samples, geologic samples, measurements, and really setting the stage for, I'd say, future history. I mean, I think history will mark not just July 20th, the day of the landing, but July 24th as a monumental moment in humans' evolution. This is a snapshot provided by the Lunar Planetary Institute of the missions leading up. The full figure goes probably about 13 feet more that way. I just snip off what happens in 1969 up to 1969. So we have each of the orbiting flyby and impact or landing missions across time. And what I'm trying to show here is that, it didn't just start with Apollo 11 in 1969. There was a whole series of impact experiments called Ranger that were sent to not just hit the moon, but to show that we could get to the moon and communicate with something as it's going to the moon. The U.S. also had the Lunar Orbiter missions, which are a series of mapping missions, all leading up to Apollo. In the midst of that also is Ranger, which were these soft landers that were giving the first insight into what the lunar surface actually looked like. It's hard certainly hard for me to imagine a time where we thought that the moon was covered in a dust layer several miles thick that wouldn't support an astronaut or support a lander, that they would just sink into. But prior to our first close-up views in 1962 and our first landings in 1964, the lunar surface was an uncertain terrain. The universe, our understanding of the moon, largely limited to telescopic observations of the near side. And so it was these precursor missions to Apollo that set the stage that made Apollo a success. So I hope that as we celebrate the accomplishments of Apollo, we also have to acknowledge the robotic missions that came before. Just in the same way that the robotic mission that I work on, Lunar Reconnaissance Orbiter, is paving the way for future exploration. I also like to think, though, that instead of needing to have 5 lunar orbiters and Ranger, we just need one really capable spacecraft in the form of LRO. So let's talk about Lunar Orbiter for a minute. Lunar Orbiter was this 5-staged mapping program, and this is from the summary report published in 1970. But basically, Lunar Orbiter was this required mission to map the moon in sufficient detail so that we could identify safe and interesting landing sites. And so the figure on the right shows hemispheres of the moon, near side and far side, and the various images that were taken. And you can see there are these small postage stamp sized spots that are mapping small areas in detail, meter or so per pixel, so that you could see hazards, craters, and boulders, as well as larger scale images of the far side. By the time the first 3 Lunar Orbiter missions had been accomplished and were successful, the subsequent 2, Lunar Orbiter 4 and 5, were turned really over to planetary scientists, mapping the entire near side of the moon and mapping portions of the far side of the moon and other areas in high detail. It was deemed that the first 3 missions had accomplished the goal of identifying and mapping safe landing sites, and so that the subsequent missions could really be turned over to mapping the rest of the moon for scientific interest. At the time, the Apollo landing sites required basically 1 meter ground resolution within areas of about 5 degrees of the equator. So we're looking at a narrow band right around the middle of the moon between longitudes 45 and 45 east and west. So really looking at a small subset of the lunar near side for potential landing sites for human exploration. Of course, what's mentioned sort of by not being included in here is, they're not considering anywhere on the far side of the moon, and certainly not considering any place towards the poles of the moon. And so this initial mapping stage for Apollo, which would set the ground for the first few missions, really focused on central near side areas of the moon. Fantastic, safe, interesting landing sites. The data that was turned into areas of interest, and so 5 potential landing sites were mapped all along the equator. Again, that 5-degree area, all on the central near side. Landing site 1, 2, 3, 4, and 5. And it basically became a question of all 5 of those places are totally interesting, would be great to send the first crew. Which one of them is going to be the safest and most interesting? This is a set of frames from the Ranger impact. Again, you have this impactor aimed hitting the moon, taking pictures every few seconds. As it gets closer and closer, we get higher and higher resolution images of the moon. And so this provides the first up-close view of the lunar surface and basically validates that there are areas that have little craters on them, but there are smooth, flat areas that we could land as well. And I'm going to step aside for a second. You can see little green circles. Those green circles, the green circles are mapping where Apollo 11 would land. So this is the first up-close view of the potential Apollo 11 landing site. Next, we have Lunar Orbiter 5, which was that final Apollo precursor orbital mission. And again, you get to find the green dot. There's the green dot in there. And the glare is a bit much, and the green dot right there. So up until Apollo, these are the best views of that second landing site. This is all we had. But at first blush, yeah, there's lots of big craters, but you don't see much in the way of hazards. And they knew, of course, that we'd have astronauts landing on the moon. They'd be able to navigate around hazards and find a safe landing site in there. This is a nadir view, an up looking straight down view of that Apollo 11 landing site. And there's the circle showing where they eventually did land. And again, lots of big craters, but smooth, flat areas, enough to sustain a 10-meter wide lander. So this landing site remained on the list of possible targets. Now, let's fast forward to January of 1969. This is the Apollo 11 crew. And at the time, it was recognized that they would have the opportunity potentially to be the first landing on the moon. However, this is just on the heels of Apollo 8 having successfully shown that we can orbit the moon and send humans at least into deep space. There would be 2 more missions prior to Apollo 11, Apollo 9 and Apollo 10. Apollo 9 would be an Earth orbiting mission to test the lunar module, and Apollo 10 would test the lunar module in lunar orbit. So those 2 missions not only had to be successful, but demonstrate that the lunar module would work. They're standing in front of a mock-up of the lunar module right there down in Houston. And that if those 2 missions were successful, Apollo 11 would be given the green light to be the first mission to land on the moon. Of course, the downside of having 2 missions in front of them is that they are waiting to use all of the resources. You have 2 other crews that have to train on the lunar module simulators, and so what do they do to keep themselves busy? Well, they do other forms of training. And I'll get to a video in a little bit that shows some of the training that they did in early 1969, waiting essentially for those 2 precursor missions to be successful. So Apollo 8 orbited the moon and imaged a portion of the lunar near side with the goal of identifying some of these safe landing sites. However, when Apollo 8 got to the moon, the second of those landing sites, I'll go back a second. So, these are going from east to west. When Apollo 8 orbited the moon, this first landing site here was visible to the crew. The rest of these landing sites were in shadow. It was nighttime essentially at the rest of these landing sites. The thought being, well, let's not worry about imaging all of these 5 landing sites from orbit. Let's just try to get the first one nailed down. Now, something that I hadn't appreciated and only learned last year is that Apollo 8 on its return to the Earth actually re-entered the Earth's atmosphere and splashed down into the Pacific at nighttime. That was deemed an acceptable risk, however, that prevented any kind of visual inspection of how the parachutes performed as it descended through the Earth's atmosphere. And of course, the crew was then left in the bobbing command module in the middle of the Pacific Ocean for several hours until the sun rose. And of course, that was deemed to be acceptable. However, for Apollo 10, Jack Schmitt, who is the scientist astronaut working very hard to prepare the crew for their trip to the moon, identified that, well, if we wait one day, if we don't launch when we normally would have with Apollo 10, if we wait one day, that second landing site will be visible, and when they return to the Earth, they'll be able to re-enter the Earth's atmosphere and splash down at daytime. And so, unbeknownst to NASA management, he had asked basically the navigation team at Johnson Space Center to come up with the data pack, the information about how that mission would work, the timeline for that mission, which cost several $1,000s, a lot of money. And he just said, "Can you just do this in your spare time? And I'll make a pitch to headquarters that they should do this." Well, we already have the Apollo 8 data pack. Why do we have to spend the extra money? And once NASA headquarters heard that they would splash down at daytime, they said, done. Oh, you already have the data pack, you already done? Okay, great, we're going to do it. So Apollo 10 was targeted to go a little bit later and be able to image that second landing site. And again, if you can play the game Find the Green Dot, here. 5 images of what would become the Apollo 11 landing site showed that at this blush, at this scale, it was free of hazards, and that in the lunar module, the crew could navigate and know where they were and follow landmarks to perform a successful descent. And so because Apollo 10 was successful, basically because NASA didn't want to spend extra money, they said, well, you've just shown that this landing site is safe. You've shown that we can splash down at daytime. That's going to become the Apollo 11 landing site, and that's it. And that was it. There was no grand science question of, oh, well, then what are we going to do? Nope, that looks safe. We have all the necessary information. We're going to go there. And so that's really how the Tranquility Base became such a famous spot, not because of any grand thought of, oh, this is going to be an important point for humanity. It was because NASA wanted to be thrifty. And so as all good geologists do, for each of those landing sites, geologic maps were constructed. I have my own copy of the geologic map. Of course, the landing on the moon occurred in July of 1969. The map wasn't published until 1970. So government still works at the same pace. But that did mean that they were able to mark the landing site right here. That's where Tranquility Base is. And for those of you that are aware of the Apollo 11 landing story, they were initially targeted to land basically right in the middle of this large crater. And so Neil Armstrong had to take over manual control and land just downrange there. This is the square right here is the rectangle of the map that you just saw, and that ellipse that's in there is the landing ellipse, basically what their target was. Of course, initially they were aiming for the dead center of that ellipse right there. However, because when the lunar module and the command module separated in lunar orbit, they hadn't purged the tunnel between the two spacecraft completely. Now the gauge said that it was 0, but the fidelity of the gauge wasn't quite good enough to show that there was still a little bit of pressure between the two spacecraft. And so when they released, it popped like a cork just a little bit and added just enough delta V, enough velocity to the lunar module where it was pushed to go about 3 miles downrange of the intended landing site. It was still where they planned to go. Neil Armstrong had still, by studying the images available to him, knew that he was on the right path, wasn't hopelessly lost. But because there were no major landmarks near where they landed, he couldn't radio up to Michael Collins or radio back to Houston saying, oh yeah, no, we're 3 miles downrange. As he was landing the lunar module, he's looking out the window, tracking the landmarks. And at one point, he had to look inside and went back and basically lost the visual connection of where he was. He knew he was safe, but he couldn't quite pinpoint exactly where he was. And only until the crew came back with the video taken on, or the film, taken on ascent, could they piece together exactly where the crew had landed. Now, let's take a step forward 50 years and talk about how we would do this today. With the benefit of data from LRO, this is a web page called LRO Quick Map, which allows you to zoom in on any point on the moon. And so I'm zooming in near where the Apollo 11 mission landed, and basically integrate and bring up any data set you want that's been collected for the moon, not just from LRO, but from previous missions as well. So I'm pulling up data from our Diviner instrument, which is basically our space thermometer measuring the temperature of the moon, which we can use to map things like rock abundance. And so we can pull up layers and so, and tell, oh, here's all the rocky areas, all those little colorful spots are small impact craters. We have the highest resolution topographic map of any object in the solar system. This is data from the Lunar Orbiting Laser Altimeter, which is our instrument that we built at Goddard and have been flying at the moon on LRO. And so, we're doing the same thing that was done with Lunar Orbiter, but now we can ask questions of, okay, well, where are the colder spots on the moon? Where are the rockier spots? We have at our fingertips much greater detail in terms of what we can not only measure at the moon, but use in selecting safe landing sites. And so, again, it's the same approach, the same philosophy. When we do send humans back to the moon as early as 2024, we don't want to be limited in just near-side equatorial locations. We want to be able to go to the poles, for instance. And so we now have an incredible data set for the entire moon. And I want to emphasize entire moon because we also would love to be able to go to the far side of the moon. And so I spin the moon with my cursor and begin to look at areas on the far side of the moon. This is a web page that's publicly available. All of the data that LRO generates is released to the public every 3 months. We've produced over 1 petabyte of data, I think 1.2 petabytes of data, the largest volume of data of any NASA planetary science mission ever. This is a crater on the far side of the moon called Jackson. I'm a big Johnny Cash fan, so I always like talking about Jackson. And again, just an illustration of what we can do with our image data as well as compositional data. These dark blue areas suggest that there's a distinct composition that reflects what we think the ancient crust of the moon was made of. And so again, we can bring in all of these different data sets. This is this rock abundance map. These red areas have lots of small rocks in them, which as a geologist is both a wonderful thing. We want to go collect those rocks. As engineers will say, stay away from those rocky areas. So it's that interplay of what do we want versus what the engineers want. Engineers tend to win the game in those discussions. But as you get closer and closer to the moon, our high resolution images come through, and just sort of a tantalizing first glimpse at what we can actually see with this wonderful LRO camera data set. Anyway, so again, the tools, the approach is very similar, but now we have this incredible wealth of data, not just from our mission, but from every mission from 50 years ago to today. So let's talk about training, how we got the crews ready to go to the moon. And as I mentioned before, the Apollo 11 crew in particular had 2 missions before it in the queue, so they couldn't get priority time on the simulators. They couldn't get time to do all of the things that they wanted to do. But they had been training since they were selected. Neil Armstrong, part of the second crew of astronauts, so they had been training, since day one for not only going into space, but with the idea of what they would do on the lunar surface. The crews, all astronauts received extensive geology classroom and field training. And Aldrin and Armstrong had the benefit of having been the backup crew for Apollo 8. Now Michael Collins was originally going to be on the Apollo 8 crew. He had some neck surgery, so he got bumped, and which worked out to his benefit. If you're going to go from Apollo 8, the best subsequent crew to go to is Apollo 11, I think. And so certainly Armstrong and Aldrin were familiar with the systems, had worked very hard on Apollo 8. And again, once they were selected in January, kind of got to go full bore. They had to wait, as I said, for Apollo 9 and 10 to prove that they could land on the moon. Everyone was confident that they could, but they had to wait for those missions to actually succeed. Now, this is there's this great archive of videos and material that NASA produced in the 1960s for educational propaganda videos. You can sort of almost in your head hear the narrator. Here's NASA's brave astronauts preparing for their future exploration of space. And for those of you that are familiar with the astronauts, there's Ed White, who would be the first astronaut to do an EVA in space, a spacewalk, Tom Stafford. And there's Neil Armstrong, before he became Neil Armstrong. And this is in 1964 doing what was sort of informally called a show and tell field trip, getting the astronauts out and just used to the idea of geology and the principles of geology. And they all loved the idea because it got them out of classrooms, it got them out of Houston, it got them away from home, it got them away from simulators and trainers. They got to go out and play and pretend and learn how to be geologists. That also included geologists' favorite sort of pastime when they're in the field, sitting around a campfire at night, having beverages of their choice, talking about what they saw. So this was how these crews got introduced to geology, and the goal was to get them at least starting to think of what it meant to be a geologist. In 1965, the next crew of astronauts did the same sort of training. There's Michael Collins looking at images of Flagstaff, Arizona, Dave Scott, who would later go to the moon on Apollo 15, and there's Buzz Aldrin as well. I'd like to say looking very interested in the opportunities presented to him. I should actually point out that the geologist here who's pointing out what he's putting out what Dick Gordon, who went to the moon, orbited the moon on Apollo 12, ended up being sort of the deputy lead geologist for the later Apollo missions. He was someone who supported a gentleman who we saw in the first video. I'll go back to this in a second here. Let's see. The lead instructor in this video is Bill Mulberger, who led the geology, what's called back rooms, for Apollo 16 and 17. There's Bill Mulberger. And so for Apollo 16 and 17, Bill Mulberger and his deputy, Ed Jackson, who we saw in Flagstaff here, sort of ran the show. But they had 5 years or more than 5 years of experience working with as astronauts. So it was not so much telling someone who's going to the moon, here's what to do. It was saying, okay, Jack, when you get to the moon, let's do this and this. So, okay, it was a very collegial atmosphere. And so they had almost a decade of experience working with these astronauts. And very much in the same way that today we do the same sorts of activities with the astronaut corps. A colleague of mine, Jake Bleacher, has been working very closely with the Johnson Space Center at getting the astronauts out in the field, working on rocks and thinking about what it means to be a field geologist, with the idea that maybe one day one of these astronauts will actually get to go to the moon. This is February of 1969, so the Apollo 11 crew had been announced and selected, and now they're doing their field training. This is the one geologic exercise that this crew had to basically practice in a, I mean, it's not exactly a lunar environment, but pretty close, rocky, sort of desolate. And so this is the one opportunity that Neil and Buzz had in shirt sleeves to practice their training regimen for going to the moon. By the time Apollo 17 got to the moon, they had done field exercises comparable to this, either in spacesuits or in, again, jeans and shirt sleeves, probably 15 times. So things had certainly enhanced and built upon what we started out with Apollo 11. But eventually, when we have crews that are selected to go to the moon, they're going to be doing the same sorts of things. We're going to take them to real geologic environments and have them not just pretend to pick up rocks, actually sample rocks, document the rocks, take images, do the things that they'll do on the lunar surface. Not shown in this short clip is the backup crew of Jim Lovell and Fred Hayes, who were the Apollo 11 backup crew. Of course, they would eventually go to the moon on Apollo 13, or at least attempt to go to the moon on Apollo 13. So it's always a little bittersweet to see them training, not only for Apollo 11, but when they were training for Apollo 13, knowing that they probably would never actually get to practice at their field site what they were practicing. But you can see, here's Neil practicing taking a scoop. Now, imagine you put him inside of a spacesuit, like a basketball. It becomes a little bit more difficult, but again, this is their one opportunity to practice in a real geologic environment. There's Fred Hayes and Jim Lovell, straight out of Central Casting. Oof. Now, they wanted to do higher fidelity tests, and so this is Neil Armstrong in a spacesuit, in the Apollo spacesuit, and he's got the same scoop. This is on the KC-135, the so-called vomit comet, and so they were able to not just replicate 0G, but 1/6 gravity. And so here's him, again, just like we saw in the desert of West Texas, except now he's in an airplane probably flying over West Texas, practicing picking up and scooping material. And you'll see the support crew come in, hold them in place as the plane does its dive and back up. And so they were able to do simulations like this, as well as simulations in a tank and a deep pool at the Johnson Space Center to try to show what it would be like, feel like, and simulate for them. As I mentioned earlier, my father had worked on Apollo, and in his reminiscence about it, he really reiterated the point that we just didn't know what it would be like. We could simulate 1/6 gravity, we could simulate all of these things, but we really didn't know how it would be like for them to move around. What would no mobility be like? And my dad, who became a physician, was very interested in sort of the human aspect of how would their bodies respond to being in this environment. And so when you do watch them or listen to their voices when they're walking on the moon, they spend a lot of time just describing what it's like to move and, okay, how did the training go? And that reinforces the idea that this was an engineering exercise. Not only how did the system work, but how did the human system respond to being in this environment? So let's cut to the chase. We actually did get to the moon, July 20th, 1969, and all of that geologic training began to pay off when you have humans on the surface of the moon practicing what we had trained them to do. And so I'm going to use a clip from a website that's going to go live in a few months that basically allows you to experience the entire Apollo 11 mission in real time. You can jump in at any moment, hear what the astronauts are saying, see what pictures they're taking, if TV was being shot at that time, what TV footage is being displayed, as well as listen to what's happening inside mission control. We're all familiar with the mission control room, sort of set up like this, but you can hear what the flight director is saying, what the Capcom is saying, what the ECOM is saying. You can jump in and move around and hear the entire room describe what's going on. Let's listen to ultimately what Buzz Aldrin is saying as he becomes the first practicing scientist on the moon.
Find the purple rock? Yep. Very small, sparkly fragments are the rock. They're actually in places. Yeah, but I could first guess that some sort of biotite. We'll leave that to the further analysis. Fine experiments. Could we get him to repeat that? Well, come back underneath. Could we get comment on the rock. Didn't you get it, Captain? No. Negative. This is Captain. It sounded to me like you said he thought it was biotite, but he's looking for more to figure out Roger. Quarter of an inch.
So you heard a few things happen there that are really...
Biotite is a brown mica substance.
Thank you, Voice of NASA.
Houston, I'm going to change lenses on you.
So what you heard Buzz Aldrin do is exactly what he had been trained to do. I can't stop the video because why stop like Apollo happening? It would feel bad. He was trained to describe what he saw. This rock is smooth, this rock is flat, this rock... And he said this rock has sparkly, shiny objects like biotite, but I'll leave that for the experts to decide. Now, that was what he was trained to do. Now, biotite is a mineral we find all over the Earth, but it forms in aqueous or water environments. And you heard the flight controller, the experiment's flight controller, chime up and say, what did he just say? Ask him what did he just say? Because they were perplexed. Hey, there's there mica on the moon? They heard him say, there is mica here, when in fact what he was saying was there's something that looks like mica. Now, what it turned out to be was impact glass, all these micrometeorites, these objects striking the lunar surface, melting material, which freezes instantaneously and makes a little piece of glass. So he saw shiny objects and said it looks like mica. Exactly what he's trained to do. And he got crushed. He got, you messed up, you... No. And so on the second crew on Apollo 12, they were quiet. They stopped. They said, well, this looks like, I think they called it Sprite or, green glass, green soda bottle. They're talking about olivine, which is a green glass. Just say olivine. But they didn't want to become embarrassed, was what happened to Buzz. What also became clear is, the flight controller asked, have him say that again. Now, that is a huge waste of an astronaut's time to have to make them say that again. No, I said it once. And so by Apollos 14 and 15 and subsequent missions, actually there was a court stenographer who was brought in to type everything in real time that was said, and those would be then published afterwards. They got most of it right, but for a court, so then they could just go back, what did he say? He said this. And so I think what this also shows is that when we do go back to the moon, and we're going to have to rely on technology. Probably not a court stenographer. Our phones are pretty good at pretty good. I do that a lot in my commute as well. I start writing if I have to think about a memo I have to write or something, I'll just recite it to my phone and it gets about 90%. But that's why most of my emails are full of gibberish, because when I say LRO to my phone, it thinks I say El Oro, like the gold in Spanish. So all of my emails are peppered with El Oro, which I think is really nice. Anyway, but you can see that there's going to be a need for this consolidating all of the data that we have, whether it's TV pictures, camera footage, everything will want it immediately. We've gotten very impatient. They had to wait months to get the TV footage processed. The film had to come back. We'll want it all in real time, especially their words. And because what the astronauts, when they're on the surface of the moon, are our eyes and ears and our mouths, and they're trained to describe exactly what they see. And I think I like to use that example of what Buzz Aldrin did, because he did exactly what he was trained to do, and I think unfairly so was kind of criticized for making what anyone would make as a normal observation. Rant over. Now, so as I said, Apollo 11 landed successfully. This is a flyover view from our LRO data. Our camera on LRO can image objects as small as roughly 50 centimeters across from our 50-kilometer orbit. Now, what we've done is placed a synthetic version of the lunar lander so that we can fly over and actually see the topography. This is that small crater that I identified earlier, that boulder-rich crater, that football-sized field crater that Neil Armstrong described as he was descending, that he had to avoid. And as he's looking out his window, he sees, okay, we're going to avoid that crater. I'm going to land long of what we now call Little West Crater, Little West Crater, and he lands long from there. But as he's flying over it, he's thinking, okay, I was trained to identify impact craters, and impact craters are important. You can see the boot tracks. This is the little scuff marks that they left while they walked around on the surface. So this is a little path that Neil Armstrong takes over to Little West Crater, and he took some pictures, collected some samples, but he didn't tell anybody that. There's this period of time towards the end of their EVA where there's quiet. And I think Mission Control just assumes, let them work. Neil walks over to Little West Crater, takes his pictures, collects his sample, and nobody doesn't say, okay, I just went over to this 30-meter diameter crater that's, or near the landing site, and I'm doing this thing. He just does it. I think one, because he knew that they'd say, oh, don't leave the area of the lunar module. They're supposed to stay very close to the lunar module. He's on the surface of the moon. He's the commander. He doesn't have to worry about going into space ever again. So he's going to do it. And it was only until they came back and developed the pictures that someone said, where did you take that picture from? It's, oh, well, there was this little crater and I walked over to it. Okay. But again, he had been trained to recognize that the impact craters were important, and so that he had to take that opportunity. There's another thing that he did that was really clever. As they're packing up and they're closing the rock box, basically the suitcase that they put all the samples into to bring home, he looks at it and he says, this looks like it's empty. We didn't come all this way to bring back a half-full suitcase. And he starts shoveling in the regolith, the soil from around him. And that sample, and NASA numbered all of the samples, 10084, becomes one of the most important samples of the entire Apollo collection, because it's about 1 kilogram of just lunar soil. And the lunar soil, the surface, the beat up topmost layer of the moon, is this rich record of the entire history of the moon is preserved there. I'll point out 2 other things. That bright spot and that other bright spot are 2 experiments that were left behind, a seismometer and a retroreflector, that we could shoot laser beams from the Earth to and measure the time it takes for the laser pulse to get from the Earth into the moon and back, so we could determine very precisely the time. Incidentally, while the astronauts are on the surface of the moon, they're shooting laser beams to the Earth. I cannot fathom that we would ever do that today. The crew would have to be, on the way home, put your head, behind a pillow so you can't be blinded by the laser. The astronauts are in the lunar module and they're pew, 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 shooting laser beams to the moon and actually measuring the distance. So this is an example of that sample, that soil sample, that regolith sample that Neil Armstrong collected. These little grids are 2 millimeter boxes, squares. And so what this represents, what this shows, is that there's a great diversity in that material he brought back. You can look at it, you can see not everything doesn't just look the same. There's bright objects, shiny objects, dark fragments. Each of those things is a different mineral, a different rock. And so these are labeled here. The thing to pay close attention to is this white fragment here, a northocite. A northocite, we now know, is the material that makes up the bright highlands, the crust of the moon. When you look at a brilliant full moon and you see the white crust of the moon, that's a northocite. That's the ancient crust of the moon. We also see fragments of basalt, volcanic rock, impact melt breccias, basically small fragments of many different rocks fused together, generated during an impact event. You see these little shiny objects. These are impact glasses, the shiny material that Buzz Aldrin was describing. So in just one scoop of material, you see an incredible diversity that represents not just the one location that they landed at the moon, but indeed fragments from all around, within hundreds of kilometers of where they landed. And so if we had only been to the moon with Apollo 11, we would have learned a lot. Now, it's a good thing that we didn't stop at Apollo 11, because there was a lot left to learn. But with this one mission, it really, again, opened the doors to our understanding of the moon. So what did those, not just those first Apollo 11 samples tell us, but what did indeed the entire Apollo 11 suite tell us? Well, first and foremost, and perhaps most importantly, that the moon is old, 4.6 billion years old. And so that constrained not just the age of the moon, of course, but the age of the Earth and the age of the solar system. We learned that the moon is dry. The rocks from the moon have essentially no water. They're drier than any rocks that we have on the Earth. We learned and really showed conclusively that impact cratering is a fundamental and very important geologic process. Before that, there was some debate as to how important impacts would be in evolution of planets. The Earth doesn't have a lot of impact craters, so how can it be that important? Well, the impact craters on the Earth get eroded over time, whereas on the moon, they remain fairly pristine. We learned that the moon, from the samples, we learned that the moon was volcanically active early in its history and really stopped having, at least the samples told us that the volcanism ended about 3 billion years ago. We learned that there are major impacts that occurred early in lunar history. And again, we don't have those impacts recorded on the Earth, so that gives us a window into the ancient history of the moon. And that the early moon was largely and likely completely or nearly completely molten. Now, how did we learn that? Well, I showed you a moment ago these anorthosites. Now, anorthosites are rocks that have essentially no iron in them. That's why they're bright. They have a lot of aluminum in them. They're a very bright mineral, a bright rock. And so one way to make a northocite is to have basically a liquid, completely liquid, and just allow that liquid to cool over time. Just like if you form, you're making ice cream. If you have something that's in that ice cream that is less dense as it cools, you'll get basically layering based on density. And so the anorthosite that we sampled at Apollo 11 suggested that the crust of the moon was made up of this anorthosite, and that one way to make that anorthosite was through an early, completely molten moon, something that we later came to call a magma ocean. And this hypothesis that the moon was completely molten is supported by not just Apollo 11 samples, but by other data, and indeed observations of other planets. So with that one sample in this paper that came out just a year after the mission, I mean, it takes me, just a year to get my car inspected. They were able to come up with a fundamental model for how planets work based on those samples from Apollo 11. And I think that's perhaps one of the most important things, is not just that the samples came back, but that the scientists had an opportunity immediately to study them in detail and publish their results at conferences and in peer-reviewed literature. So it's really remarkable. And this model now has evolved in 50 years, but largely stands the test of time. And it's not just how we think the moon formed, but indeed any solid object in our solar system. And indeed, we're looking for evidence of magma oceans around other stars. Something that I'm sure if you asked Wood 50 years ago, he would have said, no way. But of course, now this is the dominant model. So Apollo 11 was just the beginning, and this is a wonderful visualization, not just of where the missions went to, but the time that passed. And again, this is each month. So by November of 1969, we have Apollo 12 on the moon. We have a little bit of a hiatus as Apollo 13 fails in April of 1970 right there. But eventually Apollo 14 is directed to go to what would have been the Apollo 11 landing site. Apollo 14, of course, going in, the Apollo 13 landing site in February of 1971. And then the high gear of Apollo with Apollos 15, 16, and 17 with their lunar rovers and their extended duration explorations of the moon. But again, all on the lunar near side, roughly equatorial, and within a central region, which made it possible for them to return to the Earth safely. So, this is what Apollo did. Apollo opened up this new era of exploration, brought back lunar samples. It's very easy to say, well, which mission was better or worse? Well, they all built on each previous mission. Apollo 11, basically, if you put the traverse that they experienced that I showed before, you could plant that inside a baseball diamond. By the time Apollo 17 goes along, they're traveling 35 kilometers over the course of 3 days. You plant that on top of DC, they get to experience a whole suite of DC area traffic, not just huddled around the mall. They brought back more samples, brought more experiments to the surface, spent more time outside the lunar module. And indeed, actually, if anybody wants to do a nice little experiment, and I tried this yesterday, let's see. Okay. All right. Oh, no service. Well, that's why it's not going to work. Okay, well, set a reminder for yourself to wave at the moon in 2 hours and 24 minutes, because that's how long Neil Armstrong had outside the lunar module. Apollo 11's exploration of the moon took 2 hours and 24 minutes. There's the Endgame movie, the Avengers Endgame, is a 3-hour movie. That's longer than the time they were on the moon. That's impressive. That's not a good or a bad thing. That's just amazing. And of course, by the time Apollo 17 comes along, they're outside over 3 EVAs for almost 24 hours. It's remarkable. In the span of 4 years, we go from our first steps to really living on the moon for 3 days, eating, driving, on the moon. It's just remarkable. And so by the time Apollo 17 left the moon, we had also had 5 surface experiments packages that were running simultaneously. Experiments at Apollo 12, 14, 15, 16, and 17. The Apollo 11 experiments package was powered by solar power, and so it failed. It didn't turn on after the first lunar night. There was this incredible era of exploration occurring throughout the 1970s. Something that we hope to replicate in the not too distant future. After Apollo, it was recognized that there were still many outstanding questions that needed to be answered at the moon. And one way to answer that was by sending an orbiting mission, a remote sensing mission to the moon. The priority for future lunar exploration should be a polar orbiting satellite equipped with photographic, compositional, radioactive, and other remote sensing instruments. Well, you could basically copy paste that and put that into the driving documents of what LRO has to do when we're at the moon. And so fortunately, now 10 years, well, just almost 10 years ago, in June 18th of this year, will be the 10th anniversary of this, the LRO launch to the moon. And we've been at the moon ever since, the longest lived lunar orbiting mission. And I love showing launch videos because, first of all, it's really exciting. I also love watching this because I think, boy, by the time we get to do our next mission to the moon, we're going to have a high-def camera outside the lunar our rocket, not just what now looks kind of quaint and old school. Might as well be like black and white if it's this old. But this was our journey to the moon. Started from the Cape. Took us 5 days to get to lunar orbit, and we've been going ever since. We're the longest lived orbiting mission at the moon in history. Here's LRO, 120 lunar days. Mars rovers count Mars days. We get to count lunar days, basically a month. And that tells us that we've been at the moon for 120 lunar days. So that's 120 days of asking questions about the composition of the lunar surface. But because we've now been at the moon for so long, we can detect surface changes. We can actually see how the moon is changing beneath our feet. And so I want to end today by asking some of the big questions that we still have about the moon. I talked about volatiles and how we showed the moon was bone dry. Now, in 1969 and 1970, when someone said the moon is bone dry, that meant there was no water, capital N, capital O water. Well, it turns out bone has water in it. So we were right, but wrong, because the moon does have water in it. The moon is bone dry. Again, it's drier than any desert on the Earth, but there is water at the moon. There's water in the moon. We see that in the Apollo samples. And so we know that the poles of the moon, for example, are unique environments. Craters near the south and north pole of the moon are deep enough to never receive direct solar illumination. We see volatiles inside some of these craters, but not all of them. And so there's a complex story about how volatiles get to the moon, are transmitted, are transported across the lunar surface, and indeed where the volatiles may come from. Do they come from asteroids and comets, the solar wind? Do they come from the interior of the moon? We don't know the relative record of that. That timer tells me that I am about a minute or two from wrapping up. We also are looking at volcanism. I talked about how the samples from Apollo told us that volcanism on the moon went from about 4.2 to 3.1 billion years old. We see evidence in some areas that there are younger volcanic regions. We see evidence for volcanism that may have occurred 50 million years ago. And so we're learning that the moon is a much more active and was much more active much more recently in geologic history. We're seeing evidence that tectonic activity is ongoing at the moon today. Apollo left seismometers on the lunar surface. We know there are moonquakes. We know that the moon is tectonically active, but when we look at these ridges, these wrinkle ridges, these small mounds on the moon and see boulders on their surface, one process that brings boulders to the surface and exposes them is seismic activity. So we may be seeing the evidence of ongoing seismic activity on the moon. Lastly, we're looking at the lunar surface. I talked about the regolith. That's this protective layer that's at the very boundary between the moon and space. We're seeing changes. This is a ratio image, a before and after image of a 70-meter diameter impact crater with ejecta, with rays going 80 kilometers away from the point of impact. So we're learning how the surface of the moon is changing over not just geologic time, but changing as we speak. It's changing today. We're also able to look at the moon not just in black and white or optically, but through different wavelengths, different prisms that reveal subtle changes in the lunar surface that we can only measure with precise photometric and observationally corrected views of the moon. And so with this incredible data set, we're able to compile not just a more robust picture of a moon, an object that we hope to go to one day, again with humans, but an object that again is our lens through a lens that we use to look at everything else in the solar system. Just as a final reminder, Apollo explored this area, 6 landing sites all on the near side of the moon. The moon is roughly the size of the continent of Africa. We have a large volume of area to explore. The entire lunar far side is almost undisturbed. There's a small rover, the U-2 rover in Chang'e 5, landed here on the far side of the moon. But there's an incredible wealth of information to be learned by exploring the lunar far side, the poles, and other regions of the lunar near side. It's my hope that humans can be a part of that exploration in conjunction with robotic explorers, not just studying those samples in place, but eventually bringing them back to Earth. I'm going to end with everybody. Some people have seen this before, which I apologize for, but let me turn the volume down a bit here. Of course, Claire de Lune, and so this is a visualization that was produced by Ernie Wright at Goddard, who takes our data and does magic with it. I don't know what you all see when you look at the moon. When I look at the moon, I see a beautiful inspirational object. I see a piece of art. I see something that my dad's name is on through his work on Apollo. I see a career, but I also see something that should be an inspiration to everyone, not just us in the US or Russia, but everywhere. And the great thing about the moon is you can be in downtown Washington, D.C. on a clear night and see the moon. You can be in the middle of the Serengeti. You can be in the middle of the Atlantic Ocean, the Pacific Ocean, look up and see the same moon, maybe oriented a little differently. You can see the dark areas, the bright areas. You can start to see that it's a geologically interesting object. If you have a telescope, you can see a little bit more clearly. And if you go to a website, you can see all of this amazing data. The moon is there for all of us to share and explore, and I'm so fortunate to be part of that exploration, and I'm so fortunate to have been able to share that with all of you today. Thank you.
Oh, where's Tycho? Well, I'm sure there are some questions. I think we're going to have Dr. Petro back every year, especially after 2024. But my question is, how long is the LRO? Is there an end date for it, or you just keep going?
So that's a great question. The check is in the mail. So, we were supposed to be a 1 or 2 year mission. We're now going on 10 years. And just in March, we submitted a proposal to NASA headquarters. Headquarters likes to keep us honest, on our toes. What new science do you want to do? And so we proposed for a 3-year mission that would start at the end, sort of a continuation of the mission, but 3 more years for LRO that would take us from the end of this year through 2022. And indeed, in a week and a half, I'm going to be going up to, anybody know Green Tree, Pittsburgh, Pennsylvania? Nobody knows it because there's no reason to go there. Except that we're having a review of that proposal to basically justify, okay, why do we want 3 more years of the mission? I'm very optimistic that we'll do well. The questions that we got from the panel are positive, so I think we'll be approved to go on for 3 more years. Right now, we have enough fuel on board to basically manage the spacecraft for about 7 more years. So it's always been my goal, unstated, and I'll say it publicly now for the first time, that I want LRO to be at the moon and image the first U.S. landing. Not to be too, yay, rah, America, but I think it's really important that we do this. So I want LRO to be there to image the first U.S. lander on the moon since December of 1972. I'd like us to be able to be there to at least be around when humans are potentially landing on the moon in 2024. Those are my personal goals. I mean, those goals aren't going to keep us funded. Doing good science and being of value not only to NASA but to the world will also be on our side. I think when we have 10 years of data, so why do you want 3 more years? Well, I've shown you all those high resolution images, but there are places we haven't imaged yet. And indeed, we're finding new ways to use those data sets. If we take 2 images at slightly different times, you can create a high resolution topographic map of that area. We've only done that for about 5% of the lunar surface. So there are definitely things for us to do in addition to detecting changes in all of the science questions that I outlined. So I think we don't just have 3 more years of science in us. I think we've got 7 years, and it's my goal again to eke out every last drop of fuel we have. The engineers that support LRO are very clever at finding new ways to extend its life. So maybe next time I'll hear it'll be still 7 years a year from now. So like everything else at NASA, the right hand of the chart of the timeline is always pushed out, and so I'm trying to push that right hand side out as long as possible.
It seems to make sense that you would work in conjunction with what they're trying to do. So
it would make sense.
Yeah.
Doesn't always make sense, but I think in this case we're on the right side of sanity.
Other questions? And please repeat the question.
Yes, I'll repeat the question. Let's start. Yeah.
Hasn't China announced that it is going to the far side of the moon?
Yeah, so they've landed on the far side of the moon already. So in January, early January, they landed on the far side of the moon. I was at home on furlough. That's why I have my furlough, the remnants of my furlough beard. And they landed and roved, and that was an incredibly successful mission. It required a communication satellite to relay the data back. It's been a really wonderful opportunity for them, and they've actually, compared to where they were with their first near-side landing and rover, been much more communicative. NASA has worked through the State Department to talk with China about that. Now we can't do direct communications with them, but things are improving in that regard. They are releasing their data and sharing it at conferences, and so I don't want to paint it as a us versus them. We do work well in competitions, and now there is this sort of urgency to do that. They have been very clear about their goals of sending humans to the moon, and I think it's good to have that sort of initiative for them and for us.
But do you think it will inform or change what America plans to do? Because it seems to me they have a more aggressive agenda.
I should be careful. But no. It will, because they've shown that it's good and important. And again, go back to Kennedy's speech. He talks about U.S. And again, I don't want to wave the flag and say U.S., but there's a certain sense of we need to be doing these things because they're important. And we should try to keep up, because if we can't keep up in this regard, what else are we not keeping up in? And that's another important point is we're not sending these things to the moon just for the sake of science. I mean, it is science, but there's also technology development. We now know how to do things at the moon and better than we could do 10 years ago. And that feeds to us. You saw that incredible data set. We're storing, archiving, but also making available 1 petabyte of data. Managing this incredible volume of data is remarkable. Now, I think we'd love to have the problem that Netflix or Hulu or whoever else is serving data, but we are developing new ways to get scientific data out to the public very rapidly, and I think that's important too. And how we communicate what we do is critical. I'll go back, and I'll make my way back up. Yep.
On that note, in terms of education,
Mm-hmm.
I'd like to commend the Air and Space Museum's film from the 80s, The Man of the Moon Remembers, which was written by scientist Volataile, which is a superb overview of lunar geology for children. Good to see that kind of outreach. But I was wondering where the geological footage of the astronauts that you showed, where is that available?
Okay, so let me thank you for. So you asked first. You commended the Air and Space Museum movie, The Man of the Moon Remembers. Is that right? And Farouk Elbaz did that, and Farouk gave a presentation at the Air and Space Museum not terrifically long ago. And then the second was the footage. So that's a funny story. So there's this whole network of archivists who are working to restore and digitize all of this video. And so one of them is a guy by the name of Stephen Slater. He works with a friend of mine, Ben Feist. Ben actually accompanied me when I gave my first presentation here a few years ago. And Stephen has been finding this treasure trove of data. How many people have seen the IMAX and publicly released movie Apollo 11? It was over at the Air and Space. It's not the Neil Armstrong biopic. This is the kind of documentary of Apollo 11. So Stephen helped find a lot of that archival material that was used in the film. And some of that is being slowly made available through the Apollo Surface Journal website at NASA headquarters. But it's all being turned over to NASA, digitized and archived, and some of it's online on YouTube. But ultimately, like most archivists, it's sitting in hard drives in Stephen Slater's computer. Not that he's hoarding it, he's preserving it and sharing it with interested scientists, filmmakers, whomever. And so I think there's still some work that needs to be done to find out a forever home for these materials. As it turns out, the Johnson Space Center isn't exactly equipped to host several terabyte video archive. 30 minutes of watching astronauts practice is fascinating, but doesn't make for compelling archiving material. So it's web material. And so there's still some effort that has to go into finding a forever home for it. But Stephen Slater has been more than willing to share material, and I can certainly get anybody who's interested in touch with him. He, as an archivist, just would like to be credited. And so for anybody who's watching online, the historical footage is all because of Stephen Slater and Ben Feist matching that material. There's a story to be told about finding that video material. And again, as someone who's trying to help the next generation of astronauts do this, seeing what was actually done is so critical, because we have written documentation, but they're stories, and they're colored by people's perceptions and people's egos. And so to actually see how it was done, I can look and say, oh, wow. There's some great footage that was taken in, I mentioned the geologic back room. This is the support room at the Johnson Space Center. The geologists who had trained the astronauts and who were sort of, okay, we're going to go to this place, sample this. And those stories have been passed down generally. Oh, here's how it was. It was, no. You watch it, and it's like watching, I was never in a fraternity, but I imagine it's sort of what it was. There's a joyousness, a rambunctiousness, there's a seriousness, but it's collegial. It's not mission control. Roger, check, yes, this. It's, oh, look at that rock. Oh, go. There's a joy in watching them see, in that case, friends of theirs walking around the moon doing geology. And that's so wonderful. It's so heartwarming to see.
Thank you.
Yeah. Let's go to this side. I'll jump around. I'm sorry. Yeah.
You talk about using the moon as a platform to go to Mars. What's the advantage? You still got to move the same stuff to the moon, and then you got to do escape velocity twice from the Earth and then from the moon. But what's the overall advantage? Would you be able to move more bulk?
So yeah, the advantage of using the moon as a staging ground for going on to Mars, and this is, again, I like rocks. Rockets are a little bit out of my wheelhouse, but the argument has been made. Now, again, this all comes with cost. Is if we can go to the moon and instead of, all right, we have to bring everything to the moon and launch. Yeah, that doesn't make sense. Bring everything to the moon and then launch it again. What if we bring much of what we need, but build on the moon, extract titanium, extract metals, and build there. Use the resources on the moon to build parts for that rocket. Get fuel. Part of the hard part of getting off the Earth is not just getting the equipment, but it's getting enough fuel to get you away from the Earth. What if we could get enough fuel out of the water, the volatiles that are at the moon, turn that into rocket fuel, basically use the moon as a fueling station. Then if you can use that fuel there, you don't have to launch as much deeper into space, and so you do benefit from the lower escape velocity from the moon. That's been claimed as that's in the future. We have to go find where the volatiles are, find out in what form they are, how easy is it to extract it and use it. But that's the hope. Over here.
Can you talk about, you mentioned earlier historically that the Air Force was going to map the moon. And obviously the Air Force and the Army early on before NASA was formed were sending rockets and something. But is there any aspect that you know from the political, at some point it was said, all right, no, you're now going to do reconnaissance satellites or some other aspect instead of science, but as you probably know, at the Kennedy Space Center, there's a capsule that says the Air Force on it. And I'm just curious from what historical aspect you know about that break off and the political aspects of that split.
Yeah, I mean, there's, one of the things that my father taught me about his experience working with Apollo is he was also working on the Manned Orbiting Laboratory, which would have been basically a military outpost in space, staffed by astronauts, observing, flying over Russia and China, Soviet Union and China. And it was deemed very early on that having astronauts do that wasn't really all that critical, because you could have robotic reconnaissance satellites do that. I would love to have the budget that the military spends in space, because it's more than NASA's budget. I'd love to have their technology, because the cameras are better. We get their, several generation old versions. I think the split, I guess I shouldn't. I can't comment with any form of knowledge of that particular split. I think it was best recognized that NASA needs to be a civilian agency. and do things that can be shared and inspire the public. And we can't say, well, here's this thing, but I can't talk about that. And here's that it was best set that NASA be completely open and transparent, and that we let the military do their thing. I think NASA's benefit is that we can go beyond Earth orbit. And as far as I'm aware, there's no military interest in the moon anymore beyond mapping it, or Mars or anything else. And that once you get out of low Earth orbit, the interest from, or even, I guess, geostationary orbit, the interest from the military side diminishes. They're interested in looking down, we're interested in looking up. And that, again, from the astronaut side, robotic assets in space can be there longer. You don't need to keep them fed. Even military astronauts have to eat and drink every once in a while. Hopefully that answers your question. Yeah.
Based on your knowledge, is there a particular area of the moon? I thought I heard you say the South Pole.
Mm-hmm.
And then I've heard about the scorching areas from solar or cosmic rays. So knowing all this, what would be, in your opinion, the safest areas for humans to go back now?
Okay, so the question was, where are the areas that I'm interested in going, and where are the safest areas? And that was what LRO was supposed to do, is find those safe and interesting areas. Now, depends on how you define safe. Anywhere on the moon is inherently risky because you're in a spacesuit and all this stuff. Certainly near side is safer than far side. If you're on the near side of the moon, you can talk directly to the Earth. We know the equator area of the moon because we've been there with the Apollo missions, for instance. But once you get towards the poles, you get into more interesting areas because of the presence of volatiles. The far side of the moon becomes geologically interesting to me because not only is it unexplored, but just visually you see how different it is. Near side of the moon has all of these broad areas of volcanic activity, whereas the far side of the moon is far more limited. We know that the crust on the far side of the moon is thicker. We don't necessarily know why. So for me, if Jim Bridenstine walked in here, or Vice President Pence walked in here and said, yes, Noah, pick the landing site, I would say, okay, let's go in here. Let's go to that enormous basin on the far side of the moon. There's an impact crater, the largest impact crater certainly on the moon and perhaps in the entire solar system, the South Pole Aitken Basin. I'd love to know how old it is. Again, geologists want to know how old things are and how they happened. If we can date that basin, that gives us a sense of how old the oldest feature, recognizable feature on the moon is. Also pinpoints the period of time of this intense bombardment on the moon. I'd say let's go to the South Pole Aitken Basin, either robotically or with humans. But I'd be hard-pressed to say any location on the moon is uninteresting. If it were up to me, I would not send the first, second, third, fourth astronauts back to an Apollo landing site, although each of the Apollo landing sites, especially Apollo 17, in my eye, has unresolved questions that would really benefit from going back. So, but right now, the push for the first return to the moon landing is going to be at the south pole of the moon. And again, we know volatiles are present there. They have a unique environment. There's areas that are permanently shaded, but the danger from cosmic radiation, solar radiation exists anywhere that's illuminated, and it's hard to find a spot that'd be protected from that. However, there are features that have been found in images from LRO as well as from the Japanese satellite that show, if anyone's familiar with, in Hawaii or Iceland, there are lava tubes. We think we see evidence for lava tubes on the moon. Those would be incredibly challenging environments. I think anyone who talks about, we'll just go into a lava tube, that's going to be hard. They're 100 meters below the surface. You need to get down. We have no idea what the interior is going to be like. But let's think real big here. If we could use one of those lava tubes as a potential shelter, sure, it would be complicated. But, if we're going to go to the moon and stay there, we need to be safe. The other idea is that you go and you use that regolith, that material that I talked about, and you basically can bury your habitat under that regolith, and that could provide enough shielding from a dangerous radiation event. We were very fortunate. In August of 1972, there was a massive solar flare that passed across the surface of the moon. It was just between Apollo 16 and Apollo 17, but had astronauts been there, it certainly would have been a bad day for them.
Are there lava tubes at the south?
No, unfortunately. So where you see the dark areas, the dark surfaces are where we see lava tubes. And there is, the nearest extensive area of volcanism is several hundred kilometers away, and the nearest lava tube that we found so far to the South Pole is up in here. So unfortunately, not quite close enough. But again, great future destinations. Yeah.
I was wondering about the seismometer.
Yes.
Is it still operational? How often do they have moonquakes?
Okay. So yeah. So the seismometers that were left on the moon. The first was on Apollo 11. That lasted for about 2 weeks after the mission before the first sunset. Subsequent to that, on Apollos 12 through 17, different versions of seismometers were left and operated throughout the course of multiple lunar days. There was a radioactive power source, so they could just be powered indefinitely. In September of 1977, there was a cost-saving initiative to basically reduce the $1 million that was spent every year maintaining what was called the Apollo Lunar Surface Experiments Package, ALSEP, and they were switched off. So saved $1 million. Hooray! So we have that baseline of data, though, from Apollo 12 in November of 1969 through 1977 with the other missions, and we saw evidence for moonquakes fairly regularly. Small ones. I think the largest moon or seismic event was probably a Richter scale 4 event. Now, of course, right now we have a seismometer on Mars in the form of the InSight mission. Here we had seismometers working for many years. We could measure impacts, meteorite impacts, and we can tell based on the seismic signal that got to each of the stations, as well as deep interior moonquakes. There is an initiative put forward by colleagues of mine to send a seismic network back to the moon and have it go for at least 7 years, if not longer, to follow up on those observations. Again, we have a seismic network that's based on the near side. The moment we land a seismometer on the far side of the moon with one on the near side, we double our efforts and benefit of the measurements that they can make. We also did really clever experiments by crashing things into the moon. And so starting with the post-Apollo 11 missions, basically the empty upper fuel tanks from the Saturn V rocket were deliberately impacted into the moon, as well as the lunar modules. And so those served as known impact points of known energy to basically calibrate the seismometers. So we had these large-scale events that we could see in the seismic network whenever we impacted the Apollo 13 S4B stage. That was the one successful, that was one experiment from Apollo 13 that actually was able to reach the surface of the moon. Was the Saturn, the empty rocket stage impacted and was measured at the Apollo 12 seismometer. In the back, yep.
Is the orbiting vessel around the moon GPS assisted when you're taking measurement data?
So there's no...
There's only one side you can do it at anyway.
Yeah, so there's only... The way that we know where we are with LRO is kind of interesting. We had a requirement on the mission that we be able to precisely geolocate all of our measurements with an accuracy of a few meters on the lunar surface. Now, we've gotten near the Apollo landing site centimeter scale accuracy. We do that in a few different ways. Initially, we would take a laser pulse, just the same way we shot laser beams at these mirrors on the surface of the moon. Instead of shooting at the Apollo sites, we would shoot a laser from the Earth to our spacecraft. So we could pinpoint in space, in 3 dimensions, where that spacecraft was pointing down at the moon. We also have 2 star trackers, basically telescopes that point at different known stars, and we can use that to precisely geolocate ourselves. In addition to that, after we got to the moon, a subsequent mission called GRAIL, Gravity, Recovery, and Interior Laboratory, it was actually 2 spacecraft, orbited the moon, and because there were 2, they could track each other. So when they were over the far side of the moon, we knew how they were moving relative to each other. And based on our precise knowledge of where those spacecraft were in relationship to each other, construct a very high-resolution gravity map of the moon, which we can now use. And so basically with all of those different parameters, we know within a few meters of where the spacecraft is in space. We can take our data set, and when we get it on the ground, precisely basically overlay it with the existing 10 years worth of data. So for any location on the moon, when I show you those high resolution images, we know for areas on the far side within a few meters of exactly where they are, and again for areas around the Apollo landing sites within a few centimeters of where things are. So our accuracy is pretty great for that, and again that's beneficial because if we want to go to a place on the far side, we better know exactly where it is. And for future explorers, if we're going to send let's just pretend we're going to send a lander, a long duration rover here. Well, they could precisely locate themselves based on knowledge of where the Earth is, but if we're over on the far side, as you alluded to, we don't have the benefit of having kind of the Earth as a geolocation point. But with this incredible data set now, we can basically do precise navigation just knowing where we are with respect to the surrounding terrain. Not quite dead reckoning, but pretty close to that. Okay.
We should close.
Yeah.
You can all.
Thank you.
Thank